Today we're going to start section 12.2, which is all about vectors. This is a 2-day section. I'm going to try to get through as much as I can today. Tomorrow we will finish whatever notes that we didn't get to today, and then hopefully you guys will have time to start homework or ask some questions on homework or whatnot. I believe you guys have covered vectors before, right? Maybe in physics, maybe in pre-calc. Yeah? Okay. We're going to start out with the definition. A vector indicates a quantity that has both. Okay, so you guys tell me, what does a vector have? It has two measurements: magnitude and direction. Over the course of this semester, the most common examples that we're going to look at displacement vectors. We're going to look at velocity, and we're going to look at force. There's others that we're going to look at too, but those are just some examples. I want to talk about some vocab and some notation, which might be a little bit different than what you've seen before. This would be a vector. We normally give what's called the initial point. And then we also give what's called the terminal point. There's a whole bunch of different notation for vectors. You need to be able to recognize all of them. Sometimes you're just going to give a single lowercase letter. So like U. Has to be bolded though. So this is probably what you're going to see on WebAssign a lot. Personally, I don't bold when I'm writing just because it's difficult. You might see this. This is the notation I use the most. Instead of an arrow like that, it goes like this. So it just goes up, it doesn't have the down. It's just easier to write. Then sometimes you might see this, or you might see this. These last two notations are pretty common. What these notations tell you is that your vector starts at A and it heads towards B, understanding that B is the terminal point. So you're going to have to be able to recognize all of those and use all of those. I'm not going to tell you which one I prefer for you. I don't care which one you use yourself, but you need to be able to recognize them. A few different notes on vectors. We say that two vectors are equivalent. We also sometimes say equal. If those two vectors have the same length and direction. So in this case, I tried to make these two vectors have the same length and direction. So we would say that U is equivalent or equal to V. Another one that you need to be able to recognize, something like this. That's called the zero vector. You also might see a bolded zero. So bolded zero means the zero vector. This vector has a length of 0 and does not have direction. Another definition, we are going to define vector addition. We're going to look at what that means when you have two vectors geometrically and then also algebraically. Okay, so let's say that we have two vectors, U and V, that are positioned so that the initial point of V is at the terminal point of u. Then u add v is the vector from the initial point of u to the terminal point of v. So here's an example. Let's say that we have vector A and that we have vector B. If we want to do A add B, we'd need the initial point of B to be at the terminal point of A. So what we're going to do is we're going to draw A. The terminal point of A, we are then going to put B. So then A add B is going to start at A and go towards the terminal point of B. So then an obvious question that arises is what happens if we do B add A? Are we going to get the same result? So we'll do that one real quick. So this one we're going to start with B. Where B terminates, we're then going to draw A. So then this will end up being our B add A. So that tells you that vector addition is commutative. A add B is going to be the same as B add A. So these are the same. Okay, next definition. Sorry, this section has a lot of definitions and properties and theorems and whatnot. Next definition is for scalar multiplication. If C is a scalar and V is a vector, then CV is the vector whose length is the absolute value of C times the length of V, and whose direction is the same as V if C is greater than 0. It's going to be the opposite direction of V if C is less than 0. And then in the case that C equals 0, this is going to give us the 0 vector. So remember that that bolded 0 indicates a vector. So for example, if this is V, if I want to do 2 times V, it's going to be twice the length going in the same direction. So maybe something like this. If I want to do negative 1/2 V, it's going to be half the length, but going in the opposite direction now. So maybe something like this. Now, knowing that, this helps us approach subtraction. So now we can approach the case of U subtract V. Another way to look at it is if you do U add the opposite of V. So in this case, we're adding. We know how to add, and then we have a scalar multiple of a negative. Let's say we want this to be our u, that to be our v. We have u add negative v. So I'm going to start with my u. Negative v is going to be the same length, but the opposite direction. So instead it would be going down like this. And then we're adding. So we're going to connect initial point to terminal point. Questions on any of the definitions or what we've done so far, any of the sketches? Okay, before we move on, we're going to do a quick sketching example. We are going to sketch A subtract 2B. This is my A. That is my B. Take 30 seconds and sketch A subtract 2B, the vector that will be. I'm going to start drawing mine up here, so if you don't want to see it, don't look up yet until you're ready. That's what I got. You got something similar? Okay, now, this is obviously not that practical, so we need a better way to be able to represent these vectors. So a lot of times with vectors, you're going to introduce a coordinate system. Generally, what we want to do is place the initial point at the origin. Okay, so generally, we place the initial point at the origin. Once we do that, we then express the vector. There's something like this. Instead of just writing vector A, we put it in bracket notation. So that A1 and that A2, these are called components. Now, that's if we're in 2 space. We're also going to be putting vectors in 3 space as well. It's the same idea. You're just going to have a z component. So this is often referred to as bracket notation. What's important here is that these components are the initial point. Not the initial point, sorry. The terminal point. So where A1, A2, or the point A1, A2, A3 are the terminal points. Now we want to be able to write any vector. So normally what you're going to do is you're going to take a vector and then you're going to move it so that the initial point is at the origin. If you move that vector, it still has the same direction, still has the same length, so they're still equivalent vectors. So we're more interested in the case where you are given 2 points. Maybe A is x1, y1, and B is x2, y2. Then we might be interested in some vector a, which is really ab. So we're interested in the vector that starts at a, goes towards b. That vector then, you're going to do terminal point subtract initial point. So we'll do x2 subtract x1 to get your first component, y2 subtract y1 to give you your second component. And this is going to be the same idea for 3-space. Have you guys seen this before? Yes. Okay. Am I moving too quickly for us? Oh, great. If I am, let me know. Here's the example that you are going to do. You are going to express the vector that goes from point 1 to point 2. So I'm going to write it like that. In bracket notation, if point 1 is 1, 3, and point 2 is 4, negative 2. So what I want you to do, write it in bracket notation, and then I would like you to sketch the two vectors. So sketch this vector, and sketch the vector in bracket notation, please. So take a minute and do that. When you have an answer, can you compare your picture and your bracket notation to someone next to you? I want both. Yeah. Okay, sounds like most of you are done, so we're going to move on. This is what I was looking for you to get, the vector 3, negative 5. For your sketch, I wanted you to show the vector from point 1 to point 2, and then our vector in vector notation. So I just wanted us to see that these are the same vector, or they're equivalent at least. They have the same direction, they have the same magnitude. Sound good? Okay. We're halfway through what I want to do for today. Maybe a third of the way. So we might have to pick up our pace a little bit. We ready to move on? Yeah? Great. Next thing I want to talk about is arithmetic operations. Sorry, arithmetic operations. Okay, what we're going to do with our operations, we're going to do them in 2-space, same idea for 3-space. I just want to get through this a little quicker. So let's consider that we have some vector v with components v1 and v2. And then we have vector w, which is going to be w1 comma w2. Again, same idea for 3-space. Let's say that we want to add vector v and vector w. You guys have seen this before. You're going to add the components. The likewise components, at least. If you want to subtract them, it's going to be the same idea. You're going to subtract the likewise components. And then if you take one of those vectors, like v, let's say, and you multiply by some scalar, so there's no bracket on top of this, which means that k is a scalar. What you're doing is you're multiplying every component by that scalar. Okay, I have an example written down. Do we need an example with adding and subtracting vectors? No, you guys can figure out adding. Great. Okay, next one, properties. Let's see what properties you remember. First one, if I take A and I add B, that is the same as taking B and then adding A. We showed that geometrically already. What is this property called? This is the commutative, yeah. We already talked about that one. Okay, next one. If I take A and then I add the sum of B and C, that's the same as if I initially added A and B and then added C. This is the associative. Very good. Doing good so far. Let's see about this one. If I take some vector and I add the 0 vector, I still have the vector I started with. The additive identity. Is Greta the only one that's learned these?
I'm tutoring a kid right now and we're doing exactly these properties, but in 5th grade form.
You shouldn't have said that. I was giving you credit. I thought you remembered all of these.
I technically do.
Now, luckily for the rest of you, no one will ever ask you to say these ever, so I don't really know why you learned them to begin with, the names at least. If I take A and I add negative A, I get the 0 vector. You're all out on this one? This one's called the additive inverse. Additive inverse. This next one, you should all get, okay? If I take some constant C and I multiply it by the sum, A add B, I'm going to get C times A add C times B. They're equivalent. Anyone? Distributive? Yeah. We only got a few more. If I take constants C add D and I multiply by vector A, I get C times vector A add D times vector A. If I take those constants C, D, and I multiply them, and then I decide to multiply by vector A, that's the same as if I did D times A and then multiplied by C. Last one. If I take 1 and I multiply by vector A, I'm still going to get vector A. What is this one called? It's called the multiplicative identity. Multiplicative, because you also have the additive identity. Now, all of these can be proven algebraically. Because this is a Calculus 3 class, we're going to be doing some of the proofs. Now, I will tell you, on most of your exams, I'm going to put a proof. It's going to be a proof we did in class, though. Or at least something very similar. We are not going to go through and prove all 8 of these. We're going to prove the second property. So that could be on your exam. Any of these other ones could be on your exam because they're pretty similar to property 2. Okay, so what we're looking to prove is that if we take A and we add the sum of B and C, that's the same as first summing A and B, and then C, which we said is what property? Associative. First thing that we have to do is we have to define our 3 vectors. We're going to do this in 2 space. The proof would be the same in 3 space. So let's say that vector A has components A1 and A2. B is components B1 and B2, and C has components C1 and C2. If we have A add the sum of B and C. Okay, I know you guys have done, I think, some proofs in your past classes. There are 2 different sets of beliefs with proofs. What some people believe is they start with this statement and they work down on both sides until they're the same. I don't really fall into that camp. What some other people do is they start on one side and they manipulate that side until they get back to the right side. Do you see the difference of what I'm saying? Okay, that's the one that I'm gonna do. So generally when I write a proof, I only work on one side. So what I'm gonna do is I'm gonna work with this side and I'm gonna manipulate until I get here. Sound good? Okay, so what this is gonna look like, this is gonna be A1, A2, and then we're adding B1, B2 plus C1, C2. Okay, so first thing that we want to do is we want to come up with this vector. So this is A1, A2, add B1 plus C1 plus B2. Whoa. Sorry, my notation. There we go. Okay. So now I can add these 2 vectors. Here's where you're going to have to be a little careful. This becomes A1, add this whole component. So that's going to be B1 plus C1. And then we have A2, add the entire component of B2 plus C2. But really, where we want to get to is adding A and B first. So this is the same as A1 plus B1. That whole sum, add C1. And then we have A2 plus B2. That whole sum, add C2. That's the associative law. So then, this is really the vector A1 plus B1, comma A2 plus B2, added with our vector C. So this is really A, add B, and then add C. Not too bad, right? We are going to do more difficult proofs in class, but I normally won't put those on a test. Now, if I were to ask you this on a test, I don't expect you to regurgitate every single line that I get to. I think a lot of you forget to go from here to here, or you forget one of those 2 steps. That's okay. As long as you have very close, I'm okay with that. Now, do you know when you get to a proof how to indicate that you're done with your proof? QED, that's one way. Do you remember what that means in English? It's translated to basically I've demonstrated what I was supposed to. Other way that you're going to see, and this is what I do, is a box. So filled in box also means you're done. Okay, we feeling good so far about this? Great. Next thing we're going to talk about is unit vectors. The idea with a unit vector is that it has a length of 1. Okay, so in 2 space, we are going to define 2 different very specific unit vectors. The first one is I. So I is going to be 1, 0. And then you're going to have j, which is 0, 1. Remember that you can also see these bolded. You guys have seen I and j before or no?
Yes.
Yeah? In 3 space, what is the 0, 0, 1? What letter is that? So like in 3 space, I is going to be 1, 0, 0. No. K. Ooh, sorry, 0, 1, 0. Okay, so these I, J, and K, they are all unit vectors. More specifically, they are called the standard basis vectors. The idea with the standard basis vectors is that they have a length of 1, and then they point in the positive direction on each axis. So here's how you're going to see that I, J, and K. Let's say that our vector A has components 1, 3, -4. This vector can also be expressed in terms of the standard basis vectors. So we have 1I, add 3j, subtract 4k. Now this should make sense. This is 1, 0, 0. Add 3 times 0, 1, 0. Subtract 4 times 0, 0, 1. Right? This is your I, J, K. So this is another way that you're going to see vectors expressed in terms of the standard basis vectors. Okay. Good so far? I have another example with adding. Do we want to do that? No? We're good? Great. Next thing we're going to move on to. If you want examples, if this is not enough, there's examples in your book. So you can certainly go back and read those. Probably the last thing for today is norm, which I think you guys have learned before. Another term for that is magnitude. Sometimes you're going to see length. In calculus, most of the time we use the term norm. Okay, here are the different ways to show length. This is one way, looks like absolute value. Another way is a double bar on each side. And it's going to be the square root of the sum of the squares of all the components. So this will be 2 space. What example is this? Does anyone know? 3, maybe? We're gonna go with that. Thank you. Okay, here are going to be your 2 vectors. Here's what I would like you to find. First, you're going to find this. Then you're going to find this. Okay, so take 5 minutes. You have until 9 o'clock to find those 4 pieces of information. You're welcome to talk to anyone next to you if you want to check the answers or ask a question. Okay, you might not have had time to finish, but I want to make sure that we go through this before the end of class. It's really important when you look at these that you understand what your answer should look like. A, you're finding the 2 norms, adding them together. So you're going to end up with a number. B, you're finding the sum and then taking the norm. So when you find the sum, you get the vector 2, negative 2, 2. Then you are taking the norm of that, or you're finding the magnitude. You end up with 2 root 3. If you look at C, this is the norm. This is a constant then. Constant multiplied by a vector is going to give us another vector. You should have gotten V to be 1 over root 2, comma 1 over root 2. Or you could have used IJ notation. This is a unit vector. Did we notice that? Has a length of 1. Lastly here, this is the vector that you just found. You're now taking the norm of it, so you should have gotten 1. Quick thing I want you to write down before you guys leave. Process of obtaining a unit vector like you did in C and D. With the same direction. So this vector has the same direction. I guess I shouldn't put V there. Same direction as V, it just has a length of 1. Do you know what that process is called? Starts with an N. Okay. It's called normalizing. So if you were asked to normalize a vector, I'm asking you to keep the same direction, but make it a length of 1.